In this video, we're going to look at the following example. The population of bacteria in a culture grows at a rate proportional to the number of bacteria present at time t. After 3 hours, it is observed that there are 400 bacteria present. After 10 hours, there are 2,000 bacteria present. What is the initial number of bacteria? Now, as with any word problem or application problem, we're going to read this problem a few times. First, we're going to organize given information, and only after that, we're going to attempt calculations. So let's look at it again and think what we can start with. So first of all, without looking into any details, I can see that in this problem, they're talking about population of bacteria, in other words, the number of bacteria, and certain time, right? I read those words throughout this paragraph. Well, that means that we're going to be dealing with a function that represents the number of bacteria at time t. Well, let's name that function. We can choose any name we want, meaning any letter we want. Let's use n for number. So I'm going to say let n of t, right? Function of t, be a function representing the number of bacteria at time t. Next, we're going to read this problem one more time, but this time we're going to be focusing on each sentence, and actually I already prepared all that for me so that I can, again, carefully read each question and think what that means and how I can describe mathematically what it says there in each sentence. Okay, let's try it. The first sentence says that the population of bacteria in a culture grows at a rate proportional to the number of bacteria present at time t. So in this sentence, I have a few keywords. The first keyword is the rate, and the second word actually right next to it. Rate that's proportional. Proportional to what? To the number of bacteria present at time t. Now, as I find a sentence that tells me that the rate is proportional to the number of bacteria present at time t, in other words, rate is proportional to the function, it tells me that I can use the initial value problem that we saw in the introduction video. And this is how this initial value problem looks like in the general form. So it's dn dt, and here I'm using my function n, right? That's the one I named myself, equals k n. And here is that equation that pretty much describes the sentence. Rate is proportional to the function n. And then the initial condition is n of t sub 0 equals n sub 0. Let me remind you that this initial condition just describes specific function value at the specific t value. Okay, so that's all written in general, and again, that's because I have this sentence in my problem. Moving on to the sentence number 2, it says, after 3 hours, it is observed that there are 400 bacteria present. Okay, what is the meaning of that sentence? Or in other words, how can I translate it to math and describe it using math notation? Well, here in this sentence, I'm given specific time and I'm given specific number of bacteria, which is the function value, right? So in other words, I can write or translate this sentence to math the following way. The function value at t equals 3 equals 400, right? At time 3 hours, the number of bacteria is 400, right? Now, if we read the third sentence, you'll see that it's pretty much the same idea, right? After 10 hours, there are 2,000 bacteria present. So how will we translate that into math? Well, you probably can guess right away that it's going to be n of 10 equals 2,000, right? Now the final sentence, sentence number 4, is the question itself. It says, what is the initial number of bacteria? How can I translate that sentence or that question into math? Well, I need to find the initial number, right? So I need to find number, so it's going to be n. What does it mean initial? Well, initial means at the very beginning, right? When we started observing this bacteria or this culture. So when we read or find word initial, it will always mean that it happened at the very beginning of time, well, whatever time is for us. So that's when time equals 0, right? So initial value happens at time being equal 0. So now that helps me to translate it to math. So I'm going to say, what's the function value or the number of bacteria at t equals 0? Well, that I don't know. Well, that's the question, right? So I'll just put the question mark, right? That's what I need to find. Now, all that is just to prepare us for solving the problem. But that's a very good start, and I recommend you starting with this kind of annotation. Now, let's think how we can answer the question. How do I find function value at certain value? Well, it's actually easy if I have function, right? If I have function in front of me, if I have function n in front of me, then I just can plug in 0 into that function and calculate what the corresponding value is. But the problem is that I don't have function n. I described it in general right here, but what is that function specifically? So how can we find the function? Well, I can find the function by solving differential equation, right? So let's try that. I'm gonna write down the differential equation over here. dn dt equals kn. Let's try to solve that. What kind of differential equation is that? Well, it's we already talked about how it's a first order, right? First order differential equation, but specifically it's a linear differential equation, right? And if I rewrite it in the standard form, remember the standard form is when we have the derivative and our dependent variable on one side. So n is our dependent variable. So in other words, kn, I'm going to move to the left-hand side, minus kn equals 0. So now we have our linear differential equation in standard form. Remember, to solve linear differential equation, we want to use integrating factor. So the integrating factor is e to the power integral. And what function do we integrate? Remember, we have to find the coefficient of the dependent variable. Now, dependent variable is n, and its coefficient is negative k. Well, that's what we're going to integrate, negative k. Now, keep in mind that k is the constant. That's what we call constant of proportionality. But the independent variable in our equation is variable t. So that's going to be negative k dt. Okay, so let's integrate that. It's e to the power negative kt, right? And I can't really simplify it any further. Okay, well, next step in solving linear differential equation is to take integrating factor and multiply it by every term of the equation. So it's e to the power negative kt times dn dt minus e to the power negative kt kn, and then on the right hand side it's negative e to the power negative kt times 0. Right, without going into much details of the process, we know that the left-hand side is the derivative of the product of the integrating factor and the and the dependent variable. So that's n in our case. And you can always check that by applying the product rule, right? If you apply the product rule, you will end up with this left-hand side. But now the right-hand side is, well, whatever it is. So in this case, it's e with its power times 0, so it's simply 0. And to solve this, we just have to integrate both sides. So we're gonna apply integral to the left-hand side and to the right-hand side, dt, right? Okay, the left-hand side, it's integral of the derivative. They cancel each other out, so we're just left with e to the power negative kt times n. And on the right-hand side, the antiderivative of 0, well, it's going to be constant, right? You can always check by taking derivative of the constant. Derivative of the constant is 0, so that works. That looks good. And now finally, what are we doing this for? We're doing this to find function n. And I would, well, here it is. It's actually a family of functions, right? Because of that arbitrary constant. But so to put this function in explicit form, I want to get n by itself. For that, I'll have to divide by e to the power negative kt on both sides. And of course, that cancels on the left. It's just n. But then on the right-hand side, well, that e I can put to the numerator. Oh, that's kt, right? I forgot t. kt. So that e with its power I can put to the numerator, and that means that the sign of the power will change to positive. So that's going to be c e to the power kt. Okay, so as always, once we solve differential equation, or most of the time, right? When we solve differential equation, we get a family of functions as our solution. And here it is, that's the family of functions. But we want to look at the specific function, the one that really describes the growth of the bacteria in the culture, in a culture that we're observing, well, within that example, right? So we actually don't want to have arbitrary c. We want to find specific constant here. And in the next step, we'll say that, well, we don't want arbitrary constant of proportionality. We want specific constant of proportionality that describes, once again, the growth of bacteria in that specific culture. So how do we find both? Well, first we're going to take care of c. And to find c, we'll recall that we're given two initial conditions. Usually the initial value problem comes with one condition. Well, we have two conditions here. Well, because we have two constants to find, c and k. Well, we'll use the first condition, and it doesn't matter which one we use, but well, let's just go in order. We'll use the first condition to find constant c. Let me copy that down so it's in front of me here. So I'll say use n of 3 equals 400 to find c. So how do we use that? Well, we have to remember the notation, right? Notation n of 3 means that 3 represents time t, and then 400 represents function value for that t value. So long story short, 3 is going to be plugged in for t, and then 400 is going to be plugged in for n. And that will help us to find c. Let's try that. So 400 equals c e to the power, so t is 3, right? So 3k, like that. And now from here, well, I want to find c. So it means that I need to solve for c. So I'll have to divide by e to the power 3k on both sides. It's gone from the right-hand side. And then from here, c equals, now I'm going to put e next to 400. That means that I have to move it to the numerator, and that means that power changes its sign. Since it's positive here, it's going to become negative as I put base to the numerator. So that's 400 e to the power negative 3k. So what is it? This is what the constant c is. Now, of course, it has still this constant of proportionality. We'll find it as well. But for now, it's good enough. We're going to take this constant and plug that into the function. So let's see how our function looks like now. It looks like this. N equals c is 400. So I'm following this function here, but c I'm replacing with what it equals to. 400 e to the power negative 3k, and then times k times e to the power kt. Right, so that's what c is. That I can simplify a little. I can simplify it by combining bases, right? Remember, when I'm multiplying same bases, I can just simply add the powers. So here's function n. N is 400 e to the power negative 3k plus kt. Okay, and the next step will be to find constant k, constant of proportionality. So I'll make a note here, and then I'll need to start a new page. I'll say use the second given condition. It's right there above at the very top of this page. Remember, it says n of 10 equals 2000. That's when we were given that after 10 hours there are 2000 bacteria present, right? Use that initial condition to find k, and k is, okay, I don't really have much space here, but maybe I'll say it here. That's the coefficient of proportionality. So let's see. So I got more space to write, and next I will use this condition by plugging in 10 for t, right? Remember, 10 is t, that's time, 10 hours. And then 2000 for the corresponding function value, so that's n. So that's the equation I'll end up with. 2000 equals 400 e to the power negative 3k plus, now t is 10, plus 10k. Of course, that power can be simplified. It's 2000 equals 400 e to the power 7k, right? And now the goal is to find k, and we have this pretty basic exponential equation, which we need to solve by first isolating base, right? Remember from the algebra course, first get e with its power by itself, so divide by 400 on both sides. So 2000 divided by 400, that's 5 equals, and then the right hand side is e to the power 7k. And next, to get hold of that k or that power, I will apply logarithms to both sides. Since base here is e, it makes sense to apply natural logarithm, so ln. So I'll end up with ln of 5, applying ln to the left hand side, and then applying ln to the right hand side, ln of e to the power 7k. And we want to do that because now that power can be put in the front of the logarithm. So we have ln of 5 equals 7k times ln of e. Now hopefully remember that ln of e equals 1. That's 1. That means that to find k, we just need to divide by 7 on each side. So k equals ln of 5 over 7. That is the coefficient of proportionality. Let's put all together and let's look at our, finally, let's look at our function, its final version. So that's coefficient, not coefficient, constant, let's call it constant. Constant of proportionality. Now, real quick, I'll make a pause here, and I remind you, if you watch the introduction video, then you know that how we talked about if the constant of proportionality is a negative number, well, it can be either negative or positive for a specific model. Well, if constant of proportionality is negative, then we're going to be looking at the decay model. And if constant of proportionality is a positive number, then we're looking at the growth model. Well, we know that our model is the growth model, right? The number of bacteria increases as time goes by, and that is a positive number. So it is like we're consistent with the description of the situation. That's a good sign, right? Because if it's inconsistent, we have to go back and check where we made a mistake. Let's keep going. So now I'm putting all together, and I'm writing down the function. So here it is. Function n of t equals. Now where I'm getting this from? I'm getting this from here. So we almost had our function, except we didn't know what k was. We found k. Now I'm plugging in that k value into here. It will not look too pretty, but that's okay. We'll use calculator to finish this problem. So here's the function: 400 e to the power -3 times k. K is ln of 5 over 7 plus k ln of 5 over 7 t. I'm not going to simplify it too much. Maybe I'll just, put that product as one fraction. Again, I don't worry too much about this power not looking too pretty. We will be using calculator to finish this. Plus ln of 5 over 7t. Okay, here it is. Now we found the function so that we can answer the question. I'm going back to the very first page, going back to the question itself. Remember, the question was, what is the initial number of bacteria? So what is n value when t equals 0? Now we have our function to answer that. So we're gonna let t be equal 0. We're gonna plug in 0 for t, in other words, and we'll need to calculate the resulting function value. So what is the initial number of bacteria? The initial number of bacteria means that when t equals 0. So to answer this question, I'll just need to find n of 0. And that's same as plugging in ln of 5. Plugging in 0 for t, which is right here, right? That's the only place where I have to put 0. Ln of 5 over 7 plus ln of 5 over 7 times 0, right? Well, since it's times 0, well, that term is gone, and I'm just left with 400 e to the power -3 ln of 5 over 7. Of course, I'm not able to calculate by hand, but I can use calculator. So let me grab my calculator. Here it is. So hopefully you can see, but I will be literally typing in this whole expression into my calculator. So 400 e, I'll say times e to the power, and then the power itself is -3 ln of 5 divided by 7. So as you can see, I just copied down that expression, and now I'm pressing enter, and that's the answer I'm getting: 200.6787, and so on and so forth. So that's approximately 200.67876. But the question is, to how many decimal places do I want to round it? Let's refresh what exactly that number represents. That number represents, well, it's n, value of n at t equals 0, or we have the equation over here. That's the initial number of bacteria. Well, I guess we count bacteria using whole numbers, right? And because of that, I'll just round it to the whole number. So that's approximately 201, right? Okay, well, here it is. That's the answer. So that means that at the very beginning, they had 201 bacteria in that sample. Or I guess in the culture. I'll write that down. So answer. The initial number of bacteria is 201. Okay, and that's how you do this problem.